Today, my talk is about next generation multifunctional device named photo-supercapacitors for energy conversion and storage in a single compact device. So this MOBGA project is hosted at the University of Bordeaux and Institute of Molecular Science. And the findings are for the 3 years and starting in the good time at the end of 2019. Yeah. Today, my talk is divided in several parts. In several parts. I will start with the introduction, and since our devices are multifunctional, the combination of two technologies, I am going to introduce the technology A, perovskite solar cells selected as energy conversion, and then move to the technology B, supercapacitors selected as energy storage. Then a few words about the integration of technology A and technology B, and I will finish with the conclusion and with very positive prospects. Okay, let's start with the introduction. Okay, to give you more easy way to understand what we are going to do, I would like to pick up the example that I also discussed during the conference in Strasbourg last week. And I would like to start like imagine that you are in a place in the city or countryside or any other place, okay? And your phone, it's completely discharged, but you need to make or receive a very urgent call. So I think all of you already experienced such a situation. And what you will do now? I suppose you try to check your extra battery, but you found that one is also completely discharged. And you don't have any access to the power supply to charge your electronic devices. In the same time, you are in a very nice place where the sun is shining bright on you, it's abundant, free, and it will be very nice if we can use the sun to charge your electronic device at any time, any place, and as quickly as possible. Okay. Sun as other natural resources are among most effective tools we have to fight against climate change. For example, the wind, water, biomass, sun, geothermal are candidates as unlimited renewable resources to generate electricity with limited or without greenhouse gas emissions. Especially the wind and solar in the last years shown an exponential growth. So, but the wind is the formation also by sun. So from all the renewable resources, the sun is a sustainable and giant source of energy. I would like to stress on the fact that the amount of the sun strikes to the earth continuously is 10,000 times. Okay, in 1 hour is 10,000 times higher than our current power consumption. So that is a really impressive amount of the energy. But you cannot use directly the sun energy. So you cannot take the sunlight and charge your electronic devices. And for that, we need photovoltaic cells or based on semiconductor, on material called semiconductor. So we have here an example of solar cell technology. This is the most dominant in the market called silicon solar cell. And the material used to fabricate the panels are based on silicon material. And in order to have the photovoltaic effect, we need N-type and P-type silicon. For that, we need to dope the silicon with different type of material in order to have N-type and P-type. And then put together, and we form so-called junction and depletion region. It's formed automatically, and under the illumination, we extract the electrons from the material and the holes and the electron from the N side and the holes from the P side. In that case, we form the electricity. For the production of the silicon solar cell, the material itself, it is from the silica or from the sand. And then to produce very high purity silicon material is needed a very complicated metallurgical process. So where high temperature is needed to obtain high purity silicon. And then dissolution and distillation, and then specific processes in between, and then until we have the ingot, and this ingot is cut to form the wafers, and after that is the technological process to make the solar cell. And this is just one single cell from one single wafer, and then connected serial connected, we have the module at the end that is used to produce the electricity at your home, for example. Here the example. This technology is able to convert the sun energy with the efficiency of over 25% at the moment. Okay. But in the same time, there it is a problem of this solar energy there because of the intermittency. Okay, so solar cell cannot produce electricity under the cloudy or rainy days, the same efficiency like in very sunny days. So, but the electricity demand by population, by humanity, it is higher in the morning and the evening. So we have to balance and keep the energy demand and the production of the energy equally, okay? So to do that, we need, but very important to mention that the solar power generation is very stable on the Earth since the beginning of the life on it. Only technical difficulties is the transfer and storage of this energy in a very efficient way. So now let's have a look of the system that we have available for us. Now, the solar cell and the extra battery. There will be always some disadvantage of the system because of, first of all, will be very heavy and big because of the external battery, and that will affect the cost of the whole system. And there will be always some energy loss due to the cables used to okay, I put the pointer. Energy loss because of the cable. So, but imagine in the case of the solar power plants, there how much energy loss will be, like it's presented in this picture. So it's really necessary to develop single device for conversion and storage without using the cables and reducing the price as well as the energy loss. So here we have our the device that we built during the project called photo-supercapacitor, obtained by the integration of the hybrid solar cell, the last generation solar cells, with supercapacitor in the backside. Yeah. So now the solar cell is producing the electricity only when the sun is shining directly the panel. So as you can see here, this is only solar cell. However, in the photo supercapacitor, the solar cell, in the backside, we have a supercapacitor. This motor fan is rotating under the sun illumination and also when we cover the panel. So in this case, we have continuous power generation, quite compact device. So we believe this is next generation multifunctional device for continuous and stable power supply. Now let's see what kind of technology we selected to build this photo supercapacitor. We selected the most recent solar cell technology called perovskite solar cell because they are very efficient and extremely cheap, work better in the cloudy and indoor light conditions. So you can harvest the light from all the corners in your home. And it is almost the same efficiency. In the last decade, the efficiency it is growing very fast. It was growing very fast and reaching the point of the silicon solar cell technology. For traditional silicon, it took more than 40 years to be here. Yeah, so it's really impressive improvement in the field of perovskite. And also in the backside of perovskite can be easily be attached the storage device. Is the second technology that we selected in this project called supercapacitor. The supercapacitor are modern electronic device used to store extremely large amount of electricity in a very compact structure. And because of this structure and the working mechanism, the supercapacitors can be charged in just few seconds with excellent cyclic stability, and can also make easy interface with perovskite as I mentioned before. So one symmetric carbon electron can be easily attached in the perovskite. So one of the innovation of our project is rely on the use of the biomass material to obtain, and more specifically coconut shell, to obtain the activated carbon and then apply as electrodes for supercapacitor. So producing activated carbon in this way, it is environmentally friendly in many aspects. So our compact device is the integration of two emerging technology, perovskite solar cell and supercapacitor, by using a carbon layer as energy transfer layer. So we are not using cables, okay? And the device is called photo-supercapacitor. Now let's move to the energy conversion perovskite solar cell. I would like to give you some introduction and some story back behind how the perovskite appear in the field of photovoltaics. Here it is the famous NRL chart where we track every year the power conversion efficiency of all type of solar cell technology. So here I plot dye synthesized solar cells because of this technology, new technology, perovskite also appear in the field. So the dye synthesized solar cell is based on different working mechanism and different principle than silicon solar cells, and the efficiency reported efficiency is around 40%, and the certified number it is 30%. Yeah, the perovskite in some point you can see the fast growing in the efficiency. Now we are at a single junction. This means only perovskite efficiency 25.5% certified number, and as Philip mentioned last week in his talk, to absorb a more efficient way, the perovskite is attached with the silicon solar cell to form the tandem configuration. The efficiency is very close to 30%, so more precise 29.8%. So it's very important to go on the ultra high performance device, but in the same time, it is good in parallel to work for the device which can give us continuous and stable power output, and that perovskite give us this kind of possibility to integrate with conversion storage device like battery, capacitors, and supercapacitors. Okay. So let's see what is the dye synthesized solar cell. I would like to introduce you a little bit the concept and the story. In 1991, Professor Gradzel proposed a new concept solar cell. He was based on the photosynthetic process happening in the plants, and he proposed a new concept of solar cell technology. We call dye synthesized solar cell and also Gradzel solar cell. In this case, we have two electrodes, electrode 1 or N-type or negative electrode based on titanium dioxide mesoporous layer, sensitized with the dye molecule to absorb the light. Okay, and the electron number 2 anode based on the metal like platinized electrode, and the electrolyte based on the couple iodine I3 minus. I minus, I3 minus. So after the illumination of the solar cell, the dye become excited and inject the one electron in the conduction band of titanium dioxide. And then this electrode is extracted at the electrode 1 and then converted into electricity. This electron is traveling in the opposite side and then regenerated thanks to the help of a couple I minus, I3 minus, and the dye is regenerated in the initial state. So in this case, we have a closed system, okay, where we don't have any damage to the material, and it is like cycling process, okay? So why the photosynthetic analogy? Because in the plant, the first process is the same like in the dye cell. So we absorb the light by the chlorophyll, okay, in the plant, and form the electron and holes. Of course, in the plant, we have much more complicated process. At the end, this electrode is converted into chemical energy in the food for the plants. In case of the dye cell, we have also absorption of the photons from the light, inject the electron in the titanium dioxide, and at the end we form the electrical energy. Okay, this is like sandwich type technology, as you have here. So we have two electrodes sandwiched together and inject the electrolyte in between. You can make this dye cell at home. So the components of the dye synthesized solar cell is titanium dioxide. As you can see here is the white powder. You can find easily the in the composite of the paint, or some cream, bronze cream, or sometimes is additive for the food. As you can see, the powder is white, so you cannot absorb the light. Yeah, so you need the dye to attach on titanium dioxide to absorb the light. So the dye, I am sure all of you at home can make, are chemists in the morning. So you are making the tea or coffee, and then you extract the dye and you can dip that electrode. Here you have titanium dioxide electrode, white color, and dip in the dye, and then your titanium dioxide is color. In my presentation, I like to use the fruits. So here is represented the cherry, American cherry. They are very tasty, but also very colorful. So you can extract nice color. And for the demonstration, in general, we are using the hibiscus tea, and it's very efficient. Yeah, like here, this is the color of hibiscus tea, or here. Electrolyte is the iodine medicine, and counter you can make from graphite, yeah, and then sandwich two electrodes together, inject the electrolyte, and then you can make your own solar cell. So this dye technology are flexible. You can make the solar cell very lightweight in the foil type, yeah. You can imagine the thickness. It can be attached in the electronic device. Works well under diffuse light. This means under the table lamp, and can be attached on the desk. And here you have colorful solar cells, and also because of the printing technology, you can print any kind of favorite picture, like the printing technology used to print the picture on the t-shirts or the clothes. And then it is quite easy to have your own solar cell in beautiful way. Yeah. So now here it is one example where gradual cell really helps. In 2011, all of you remember the tsunami attack in Japan, where the people were really under the all of them, almost all lost the house, and then they stay in the evacuation centers. But there, because of lights in the room, it was needed to think about how they can keep their own groups without disturbing another group. So in that case, the scientists from Japan assembled the dye cell as it's represented here, attached with the LED lamp, and during the day this solar cell charged the battery inside, and during the night they could use the specific groups without disturbing another groups. Or in the stairs, this lamp was installed there to help them for the life during this period. So this is the example where the science is really helpful for the people. Here we have the transformation, general story about the transformation from liquid type dye cell to solid type. This is general cross-sectional view of the liquid type dye cell, where we have, you can see the porous titanium dioxide, the thickness about 10 micrometer. We need this thickness because it's like sponge. We need to absorb high amount of light, and we need to have high amount of dye also absorbed in the porosity. And electrolyte, since it's a liquid, all of us from the field try to solidify to avoid any kind of linkage and improve the stability of the liquid type solar cell, dye cell. Then at that time, it was discovered so-called spirometad, the whole transport layer, to solidify the electrolyte. And then in that case, because of the big molecule, the thickness of titanium dioxide was decreased to 1.8 micrometer, and the efficiency, of course, dropped down because we have less absorption of the light, and everybody, all the scientists in the field, tried to solve this problem by looking for high molar extension coefficient of the dye. The dye then can absorb more light, and exactly in that time it was discovered perovskite. To be honest, the perovskite material in general, like for no photovoltaic application, it was new material. But in that time, this perovskite was just picked up and tried to synthesize titanium dioxide mesoporous layer. And later it was proved that we don't need this mesoporous titanium dioxide to have a highly efficient just thin film perovskite on the compact titanium dioxide and this whole transport layer, as I mentioned now. So now the efficiency is over 25% in just this configuration. So this is really the story back behind of discovery of perovskite is coming from the dye cell technology. So the perovskite is based on the name of perovskite is based on the calcium titanate, the mineral discovered in Russia by Gustav Ross, and then a name thanks to the Russian mineralogist Lev Perovsky. So all the material similar to this structure, ABX3, is called perovskite. In case of the A, in our case, in the hybrid, we have methylammonium cation. In the B side, we have lead. And in the X side, we have iodine, but this iodine can be changed with any halide, like bromide or mixture, iodine and bromide. And then we can play with the band gap of the material by changing the composition. Okay. So the perovskite structure is like similar, can be cubic structure or tetragonal structure, like it's represented here. The first report, it was in 2006 in the conference by Dr. Kojima from Professor Miyasaka group, in the conference where he presented first time the possibility to apply this perovskite material in dye cell technology. The efficiency, it was not so impressive. So the bromide type perovskite, he got 2.2 almost percent efficiency, and iodine type just 0.36%, very low efficiency. 2 years later, he reported even worse results for bromide, 0.21 and 0.37 for iodine perovskite. But in this case, it was solid type. Yeah, in the first report, it was liquid type where the efficiency, the solar cell was not stable. So getting the photovoltaic response, it was in a very fast way. So he measured the device in just a few seconds. 2 years later, he could measure at least the solar cell in more flexible way. I mean, not in such a fast way. Okay, so, but after the discussion in many conference, Professor Miyasaka discussed with the community, and then, yeah, this is the Jack's paper when they could improve the efficiency to over 3%, but again, it light and they could not make it stable. So Professor Miyasaka presented this result in the conference, and since it was the time of solid type dye cell using the Spiro method material, then later in 2012, together with Henry Snaith, they published a paper in Science and reported solid type dye cell with the efficiency of 10.9%. And now we have 25.5% using Spiro metal whole transport layer. So you can see here the cross-sectional view of perovskite solar cells, where we have mesoporous titanium dioxide, where also perovskite is infiltrated inside. And here we have Spiro metal layer and the back contact metal, gold or silver, in this case silver. So N-type titanium dioxide, P-type Spiro method. And then to make the perovskite solar cell, it's quite easy. So here I present you one-step deposition of perovskite. Here we mix up the precursor PB chloride or methylammonium iodine in DMF and then spin coat on top of the conductive substrate or on N-type titanium dioxide. And then anneal at 120 degrees for 45 minutes, you can get such a nice perovskite film. And at the beginning of the work, when I start working in this field, we found that dry conditions is very important to have homogeneous film and highly crystalline perovskite. And from the X-ray characterization, we confirm we have tetragonal perovskite. So we have two peaks, 110 and 220 characteristics for perovskite structure. This is the cross-sectional view of the device that I could optimize so that we have very, as also Philip mentioned last week, the interface are very important. Interface engineering of this device is very important to have high efficient solar cell. So here I try to optimize the process and building the cell using different substrates like a rough substrate and flat substrates, and I could get higher efficiency in the flat substrate because of better interfaces. Here, the titanium dioxide, this is a planar structure. Titanium dioxide is just 50 nanometer, perovskite 350 nanometer, spirometad 300 nanometer, and the gold layer 80 nanometer. And yeah, if we are looking in the commercial silicon solar cell, so as I mentioned, in perovskite we have 350 nanometer perovskite, but in silicon we have 200,000 nanometer. And the efficiency of perovskite is equally like silicon solar cell. So that is very, very important point for making a device with very thin absorbers or photovoltaic material. Here, another process is co-evaporation, where I did in Freiburg. This method, we can build the perovskite crystal under the vacuum. So we are using two sources, one for methylammonium iodine and another for PbI2. And then using different temperature, we can evaporate and then we form the cloud. And then the cloud can easily be attached in the substrate, in this case, titanium dioxide. So the evaporation system, it was inside in the glove box, and also the fabrication, the next layers, we could perform in the glove box using the spin coater to complete the device. So the advantage of this method is that we can make several samples in once. We can evaporate the perovskite, in this case, 25 samples, very homogeneous, like you see here in the cross-sectional view. The device perovskite is quite flat on top of titanium dioxide. And also we can evaporate perovskite in texture silicon or any other substrate surface homogeneously. And that is advantageous for making tandem solar cell device. And we confirm we got tetragonal structure from the TM measurements and from the X-ray measurements. Now, another advantage of perovskite is that this device, together with the dye cell, works well under the ambient light. So here we have different light source, like standard AM 1.5G, representing the solar spectrum. And we have in the orange spectrum of white LED, and we have green and the compact fluorescent light, and blue radiated halogen light. So depends of what kind of band gap of material we are using, the solar cell can work differently. So in case of perovskite, reported efficiency at the moment for the band gap of 1.55 electron volt, reported is 25%. For the dye cell, this is under the LED light. Under the compact fluorescent light, dye cell perform well with the efficiency 30%. Okay, but theoretically we can go up to 40% for perovskite and dye cell 45% under the indoor light conditions. And there in the literature we found some papers were already proved then how is the efficiency of the silicon solar cell, commercial silicon, in comparison with the dicell and perovskite under the LED light and compact fluorescent light. So you see there it is higher efficiency compared with traditional silicon. And the same situation happened when we use different type of light source, AM 1.5G, silicon is dropping fast comparing with the perovskite and dicell. One of the problem of the perovskite solar cell is the stability. There it is very famous process happening during the illumination of the solar cell. The gold layer, it is diffusing inside in the spirometad layer, and then it's damaging the device, and also the device are not stable. Moreover, in the spirometad, usually we are using some dopants to increase the mobility. And that dopant also is very sensitive to the humidity. And then by absorption of the water, the lithium, it is degrading the perovskite layer. So there was so many work to improve the stability, for example, by changing the structure of spirometad layer, introducing different species, for example, fluorine. And then this fluorine type spiro, it is more hydrophobic, and then we can remove the water. We are not taking the water from the air. Or another possibility is to just remove spirometad and the gold layer, and then screen print on top of the perovskite carbon. And the efficiency for the moment standard type perovskite, we are on the average around 50%, but very high stability. So over 10,000 hours, it was already proved. And that is very advantageous for our system because we need the illumination long time and the convert or taking the charge longer time. And then store it in this storage device. So we are working the carbon based. Now, as I mentioned at the beginning, our project is hosted at University of Bordeaux, and also we have a possibility to use a very specific platform called the LorPrintec, which is unique in France. The size is 815 square meter clean room, where we can work under the controlled temperature and relative humidity conditions. Inside we have 5 clusters representing different integration levels like chemistry of functional material, deposition and patterning, device fabrication, characterization, and upscaling. So here you see all the facility that we have inside. And for our perovskite, it was specially adapted, special equipment to build a high performance and high stable device. So for example, we have the chemistry of functional material. We have semi-automatic reactor, flash chromatography. We have also linear transfer line that allow us to transfer the samples or the material from one deposition system to another one without breaking the vacuum. Okay, and of course there are so many technological printing pilot plant fabrication like inject printings, spin coating, slot die, and so on. Making the perovskite, we start from the deposition of tin oxide layer instead of titanium dioxide because it's more stable, and then using two-step deposition of perovskite, first layer spin coating PBI2 on top of tin oxide layer, then converting the perovskite by spin coating methyl ammonium solution and anneal at 100 degree for 45 minutes, and then to assemble the p-type, we are using general spirometad layer, using the dopants lithium, TFSI, and cobalt, and then evaporate the gold on top to form standard type perovskite. And that we need because we need to know the level and what point we are in order to compare without carbon, which is carbon layer. It is prepared by screen printing method on top of perovskite directly, without spiro and without gold. So this is the structure of the carbon-based perovskite. And the standard process is already optimized samples. We have stable and reproducible perovskite solar cell, seal device. I mean, we try in Bordeaux, it's quite humid, but we try to keep the sample stable by sealing. And we use the wires to measure, to make the contacts. In case of the carbon, we have a very stable device, but still working to improve the efficiency and be in the good level like standard process. Now let's move to the storage part, the supercapacitors. For the storage part, we have many types of storage device, and here we have so-called Ragone plot, where we can monitor the power density versus energy density of different storage technologies. For example, capacitors are with the high power density, but lower energy. Okay, supercapacitors are located in between in the middle. We have higher power and reasonable energy density, battery high energy and low power density. So we selected the supercapacitors because we can attach easily with the perovskite and can be charged in a very fast way. And to make good supercapacitor, we need very porous material for electrodes. And stable, of course, stable separator that is used to separate two electrodes, and the electrolyte with wide potential window to be able to power some electronic device. This is the device that we are aiming to build. Okay, so perovskite together with the supercapacitor, and here is the carbon bridged electrode. So in general, to obtain the activated carbon can be extracted from the coal, from the mine, but this is the technology can alter the landscape and damage ecosystems. And we want to keep the carbon under the ground, but the biomass is widely available material. Here you see some examples. Yeah, so we have then the biomass, the advantages, and we have porous material, since the nature is growing such a material and making the activated carbon, it is more easy. Some study already proved that the greenhouse gas emissions in case of the coal extraction, activated carbon production from the coal is more high than in case of the biomass. In general way to make the activated carbon, here is one example. For example, from the orange, we need to dry it, and then under the pyrolysis, we make the charcoal and then activate by, in this case, COH chemical, using chemicals, COH in this case, but we can use H2SO4 to make a very porous material. That the process, it is advantageous for making high porosity material, but the disadvantage is that we need to wash the product at the end to remove the chemicals, and that there is the corrosive process and affecting the environment. Okay, so in our project we are using, thanks to the collaboration with Sri Lanka. In Sri Lanka there are so many coconuts products, and thanks to the collaboration from National Institute for Fundamental Science from Sri Lanka, Professor Kumara, the group, he developed a very efficient way to obtain the activated carbon. So from the coconuts, first drying, cleaning, then burn it, okay, and then the process after the obtaining the biochar, the process was divided in two routes. First route, activation using the water. So in the pyrolysis process, we pass the water to form activation carbon 1, named 1, and after several time activation, activated carbon number 2 was obtained in this case. And the route number 2 and the pyrolysis, in this case, the activated agent is used steam, and depends of the how long we keep the pyrolysis. In this case, we have 3 types of activated material: AC3, AC4, and AC5. So AC5 was produced after 2 times activation. Okay. So from the characterization of the activated carbon, we found then we obtain the graphite type activated carbon, as you can see here in the X-ray measurement, to specific peaks from graphite material. In case of AC5, we see this peak then is quite large, so that saying then the activated carbon, it is amorphous type, more amorphous, but AC5 from the porosity show very high surface area of very close to 2000 square meter per gram. But the sample AC5 we selected to make storage device because of the porosity, but sample AC1 show very high conductivity, and that can be used to make the electrode for perovskite. So depend of what kind of application we have two different material and can be applied for different to build different technologies. So then we assemble the supercapacitors by using two electrodes, activated carbon, two electrodes, and then a separator. We try to analyze filter paper and the polyethylene separator and inject inside the electrolyte, aqueous type or ionic liquid. And then evaluate the storage device by measuring the capacitance, energy, power, and stability. Here, the first test, we wanted to see from all the material what activated carbon is more efficient in the storage device. So from the CV measurements, you see the blue curve, the CV curve for the AC5 activated carbon, it is higher. So that is because of the higher activated higher surface area. And here we plotted the surface area versus the capacitance of the device. So you see it is proportional to the surface area and total volume, pore volume of activated carbon. So this AC5 show higher performance, storage performance. And again, I want to remind, and this activated carbon was prepared by using the steam as activated agent. Okay, and then we use that activated carbon for the next optimization steps. So for the optimal conditions, this is the structure of our supercapacitor. We have expanded graphite like substrates because of the cost, yeah, and then they can be flexible if we change the thickness of the substrates. They are also very conductive. And the activated carbon is printed or on top of expanded graphite. And ionic liquid, we selected 1-methyl, 1-propyl pyrrolidinium bis fluorosulfonylимide, and shortly we call MPPI FSI. Okay, this ionic liquid can is having high operational potential window up to 5 volt. We can go to charge the supercapacitor to 5 volt. Is not volatile nature. We are not using any solvent, and show excellent thermal stability. Separator, it is the polymer type because it is good insulator with low resistance, the thickness just 7 micrometer, and that give to the sample lightweight and long stability. And this is this assembled supercapacitor, sealed also. We are using the UV curing acrylic resin to seal this supercapacitor. And one example why we changed the ionic liquid, here you see the CV curves and showing the potential window for the aqueous type electrolyte. We can go to 1.23 volt. In case of ionic liquid, we enlarge this potential window up to 5 volt. And because the energy, it is direct proportional with the square of the voltage, once we increase the voltage, we also can get higher energy and high power. So as you can see here, the storage device builds, so having higher voltage in case of ionic liquid device, we can increase 30 times energy and 10 times the power of the device. This is the summary of the storage device ability. Our assembled assembled supercapacitor using polyethylene separator and filter paper. And the black dots, we have the reported data using almost the same conditions like we have in our device. So we are not so bad comparing with the literature. Moreover, we can keep ability for charging the capacitance and high storage properties of supercapacitors by changing the discharge current. So that is very useful for the application. And the importance of the our supercapacitors are also very stable. You can see here the efficiency of the the retention efficiency of the supercapacitor is 92.3% after 5,000 cycles. So they are already optimized and ready to be integrated with the perovskite. But of course, also we care about the environmental impact of the production of activated carbon. So here it is we selected the production of activated carbon to analyze the life cycle assessment to produce the activated carbon with the highest surface area. And we found that the activation process of the carbon is have a higher impact. But to mitigate this impact, the life cycle assessment was analyzed with the production in France, taking consideration production of the activated carbon in France. And then that it was more efficient because of the energy mix used in France, comparing with Sri Lanka. And from the literature, if we compare with the literature data, the global warming from the production of activated carbon, but taking as a functional unit the 1 farad capacitance, we are not so bad. So our activated carbon is rated favorably in comparison with another electrode material reported by another groups. Here we have one video just showing you how supercapacitor is working. Now it's discharged, completely discharged, and we try to charge using 10 seconds using the battery. And then to verify this charging, we use the multimeter to measure the voltage. So this is already charged supercapacitor. And then to discharge, analyze the discharging time, we use different loads: red LED light, yellow LED, and blue LED. So you can see for the discharging time, it is more than 180 seconds, so more than 3 minutes. So charging is just 10 seconds, but discharging time is 3 minutes. I want to highlight here that the amount of the carbon used to build this supercapacitor is just 3 milligrams. Now moving in the integration of technology A and technology B, we are at this stage. So here we plot and the red dots, the overall efficiency of the integrated system and efficiency of photovoltaic solar cell reported in the literature, and these highlighted dots are our results. So we have some progress. Now we are in the record efficiency for the wire connection device still, and our next target is to, take these two dots up and be around here. Okay, so at the end, so this I think is the conclusion. At the end, our compact photo supercapacitor, it is the can produce continuous power generation by the combination of two emerging technology, perovskite solar cell and supercapacitors, by using two renewable energy resources, the sun and the biomass. And if we are looking the thickness of a complete device, imagine a paracetamol tablet, and it is like same thickness like paracetamol. And at the moment, the activated carbon used to rotate the motor fan, as you have seen in the video, is this amount from this tablet. And our next target is to improve the efficiency of the system, of course, and by designing a bit, by changing a bit the design, and use this amount of activated carbon to be able to charge a portable electronic device at any time, any place, and as quickly as possible. So this is the end, and I would like to thanks to all the collaborators, and special thanks to our PhD student who is working in the MOBGA project. He obtained almost all of this data. Professors from Sri Lanka who give us the powder, activated carbon powder, and for all the national and international collaborators involved in this project. And thank you very much for MOBGA fundings, and thank you very much for your attention. Hello.
So hi, I don't know if Helmut is still here with host permissions. I do see him with the attendees, but not here with the panelists. So or the co-hosting. So yeah, thank you very much, Ludmila, for this nice presentation. The presentation is now open for questions. So if there are any from the attendees or other panelists, please don't hold back and ask away to Ludmila. Actually, I can allow Helmut to talk. So now I accidentally muted you. Now, okay, there you go.
Oh yeah, thank you very much, Ludmila, for the exciting talk. There seems to be a very rapidly moving field of these solar cells and energy storage. Is there already any technical application, or is this in the early stages? I couldn't really follow whether I overlooked something or not.
So, well, you mean a real application in general or real application in our project?
No, whether this idea of converting solar energy, whether there's already technical applications outside, or if it's too early still.
The early stage, I think, is proving the concept at the moment. So we have to still working and understood the systems, the combined system. And there are with the wires, I think, wire connections, yeah. But not yet on the market, because perovskite is not yet on the market.
Okay.
Yeah, so there are die cell together with the storage device using the wires in the market. Yeah. But in case of the perovskite, we don't have yet any examples in the market.
Oh, okay, thank you. I can't see anybody, so whether there's question, maybe Philip, can you arrange this, because I'm only seeing black screen and no hands and no chat.
I actually do have a few questions here in the chat, so let me go from the first. That is from Alain Léger, who asked, "What is the half time of the device charge?"
What will be? Sorry, I did not.
The half time of the device charge.
Well, so device charge. So depends what kind of storage device you want to use. In the case of supercapacitors, in general, the charging time is very fast. Yeah. So we need just a few seconds to charge your supercapacitor. In case if you are using the battery, in that case you need more long time to charge the battery. But also it takes long time to discharge. Yeah, you can take this power long time.
Okay, so I can allow Alain to very quickly ask if this answered his question. So
yes, please. Yeah.
Alain, did this answer your question? I gave you speaking privileges.
Alors, oui, vous m'entendez?
Yes.
On ne s'est pas compris. Ma question. Oh, sorry. You want in English?
Yeah,
I think for the international, it would be better in English.
My question is, how long does the charge, when it is full up, how does it keeps in time? In other words, is it a way to make solar energy continuously available from one day to another, let us say?
Well, so again, depend on the system, yeah? So we are aiming to charge in the fast way and use long time. Okay.
What do you mean by long time?
I mean covering long time under the day, or in the evening, or in the morning.
Is it 25 hours or is it?
For the moment, it's not
hours?
yet on the market. So yeah, we try to enlarge, or we try to use the system as long as possible.
Of course.
Depends of what kind of load you are using, yeah? Or what kind of electronic device you are using to connect to this compact system or to this system. So if it is needed high power, for example, one sensor, in that case, we need high power in the short moment, yeah?
No, this is not a question. My question is, can we put that after a solar cell, for instance? And then be able to use the power from the solar cell during a full day or a night?
Yeah, so, as I mentioned, and the solar cell can convert efficiently, especially perovskite and dye cell, even in the indoor conditions. Yeah, so you can charge your storage device by harvesting the light from the room, from
So I mean, maybe I guess there's a very slight misunderstanding here, and that is how long would the charge stay on the supercapacitor? So would it discharge on its own? I think this is what is really the issue, and long-term storage. So if you would disconnect it and you would, store it away, can you come back after a month, and how much energy would you have lost by then?
Well, so then we are trying to analyze that. Okay, so it depends of how good is your storage device, how you are building that.
Okay,
of course, yeah.
Yeah, I understand we are in the beginning really, and at the forefront there. So with this, then I would like to go actually to another question that came in, otherwise we will not get to it. So and this question would be from Bernard Makisunga, and he thanks you for a nice presentation and technology. He's grateful for consideration of activated carbon to the environment, but what is the impact of lead, and particularly lead iodide, once disposed to the environment after use? Hello? Hello, can you hear me?
Hello, I am here.
Okay, all right.
I think the connection from my side.
Okay, all right. So I can repeat the question very quickly, or maybe you see it also in the chat. So Bernard is thankful for the consideration of activated carbon. His concern is about the impact of lead and lead iodide once disposed into the environment after use.
So there it is a very important topic in the perovskite solar cells. So all of us try to somehow remove the PB or try to have solar cells without PB, but at the moment the highest efficiency it is with the PB based perovskite. So there are many trials in the field by perfectly seal the device. Okay? And it's still ongoing work on the perovskite, but I think there are the solutions. The solution are there. So we need good encapsulator material to well seal the device and take care about that kind of PB damage on the environmental damage. Yeah.
Yeah, so yeah, thank you for your answer there, Ludmila. I get this asked a lot as well. I think even in my seminar 2 weeks ago, we had a similar question. Yes. And I mean, we always need to keep in mind that they are lead-based, but the films are very thin. So the amount of lead is actually minuscule. And there are no ways, as you just have put it, for lead sequestration once they would break. Okay, so let me see if there are further questions, because other than that, I think we are reaching the end of the seminar time. I don't see any further. I see that Subu actually wanted to talk about long-term storage as well. So hi, Subu.
Thanks for the talk. That's really interesting to see. And I think I like the size you showed of the paracetamol tablet.
So
If it's batteries, I mean, I guess, but on the other hand, I think everybody knows the paracetamol tablet. So it's very easy to, so what's the, I mean, so we're really talking about small quantities, right? Like small consumer devices or cell phone charging or something like that, right? And so, I mean, I think to some extent when Philips said, well, it's just a small lead cell, but really we're talking about, I mean, the C232 batteries, for example, you get like, I don't know, billions of them produced each year or something like that, right? And so I suppose there is a sustainability angle to it. Once you hopefully reach enough production, then you get, so I guess, it's sorry if I missed this in your talk, but what's the largest, sort of capacity, largest, motor that you would see this being used as? Like a 5 watt, or is it like, we're talking about like 100 watts? The LEDs are pretty small wattage, but what is the typical power rating that you'd expect this to run?
Well, yes. So, of course, by increasing the efficiency of the storage device, we have to increase the size of the storage. So in case of, at the moment, we are speaking about the flat type or plain type storage device in the laboratory scale. So we are, as I think I can use this slide, right? I can share maybe the slide again.
I guess so.
Yeah. For example, in this case, can you see the slide?
Yeah, see it.
So we are at this stage of the energy density. We are at around 100, say roughly, watt-hour per kilogram. Energy built in the lab scale for the 3 milligrams of activated carbon. If we want to increase this number, we have to increase the size. This means for the storage device, we need to think about the rolling design. That's why I say, in order to have a possibility to be able to power some small electronic device, we need to think of the storage device. Okay. So the storage device size is very important as well.
Okay.
Sorry, I guess I was just thinking of, these are common. I mean, I'm just going back to the old days of, of the D-cell batteries for radios and whatnot. And I guess that's what you're also thinking about. I mean, the bigger the battery, the more energy you can store, I suppose. But that has other issues?
Yes, it's true. That is true, yes.
But does it have other downsides? If can you just build as big a battery as you want and still maintain the same efficiency and
well, but now it is a lot of progress in the side of the battery or the storage device. So you can see, if you can imagine the previous years or many years ago, your phone, it was very heavy because of the battery. Now we have very tiny battery technology. I mean, very, very thin battery. The technology improved a lot. So, and I am sure now to decrease the thickness, it's needed to go for the solid type battery. Yeah. So I cannot open more discussion on that side, but there it is really the technology advanced. The technology was advanced a lot in the last years and will go more even. So if we can prove that we can connect both devices in a very efficient and compact way without using the wires, and both devices are quite small but can charge a lot of charge, then will be great.